Thank you, Alo. Thank you, Professor Mishra. I welcome you all to this particular session. This is actually the last technical talk of the day, and it is my distinct pleasure to call upon Professor A. Ravi Prakash Rao to deliver the talk. And as Ravi starts sharing his talk, I just take 1 minute to introduce him, though he doesn't need any introduction to this audience.
May I? Thank you. I think I've been observing that it works well if you upload the slides that I already sent, Professor Mishra. And I will then, of course, request next slide.
Absolutely, will do. Yes. While Professor Mazumdar is introducing, let me do the default in the background.
Okay, so, yeah, thanks, Ravi. So Professor Ravi Prakash Rao is an world authority on the atomic and molecular theory from Louisiana State University, Baton Rouge. And for the last 2 decades or more, he has also been deeply in the physics and mathematics of quantum information. He has been working and writing leading papers on that. Ravi has also been deeply connected with TIFR. In fact, he started his professional career at TIFR. And I also had the privilege of actually co-authoring a couple of papers with Ravi. So today, Ravi is going to talk about universal 1 by R square potentials at short and long range, avoids collapse, holds quasi-bound state. So floor is yours, Ravi, and I will caution you at 20 minutes. It is 25 minutes plus 5 minutes of discussion.
Thanks, Indranil. Thank you. And I want to thank all the organizers for having me participate in this very interesting gathering to commemorate the life and contributions of a great physicist, and also, as you've already heard, a great teacher to many of us. So I, as Haridas and others have already pointed out, had Ashok Mitra probably as my first physics teacher, as I regard, during the BSc Honors and MSc at Delhi in the 60s, where, again, as observed already, he taught in our class mathematical physics and quantum field theory. In fact, to this day, quantum field theory is not only one of my favorite subjects, and when I teach it, I still dig back into the notes from Professor Mitra of those days. We were very fortunate, I think, in Delhi in the 60s at that time to have a group of very fine physicists and teachers. Some of these names were already mentioned in Professor Panchapikeshan's first talk. And I've just listed a few, and of course, his name included as one of the teachers. And it was a great personal pleasure to see, after more than 60 years, he start this 2-day proceedings. Now, I did not actually work in research with Professor Mitra at that time, though, of course, we were all well aware of his great contributions to three-body physics. But in an irony, when I went to do my PhD, I ended up working with Professor Ugo Fano at the University of Chicago. And in fact, I was his first PhD student. And it turned out that we worked mostly on three-body systems, now in atomic physics, and in particular, either the breakup of a three-particle atom, so into a positive nucleus and 2 electrons, or into doubly excited states. And of course, you can think of the simplest systems of the negative ion of hydrogen and helium, but in any atom. So the idea is to have a nucleus and then 2 electrons. And typically, 2 electrons very slow. Either they're just leaving the nucleus above threshold after the breakup, or they're in very high double excitation. Both electrons are excited away from the ground state. Now, as you can imagine, with Coulomb forces between all the pairs, and these are long-range forces, there are some very, very strong and interesting correlations that develop in this three-body system. Now, later, it is interesting that, in fact, in collaboration with our chair, Professor Mazumdar, and Bhasin, another of the proteges of Professor Mitra, we have worked on similar things in three-body nuclear systems, which is, of course, coming closer to Professor Mitra's own contributions in the three-body problem in nuclei. Next slide, please. May I move to the next slide? Yes. Now, unfortunately, I do not have slides of any association with Professor Mitra going back to the Delhi days. But in 2010, again, with Professor Indranil Mazumdar as one of the principal organizers, there was a session at TIFR to honor both Professor Mitra and Fadeev, who are, of course, the two names for their independent work on the three-body system in quantum physics, and sort of set the stage for how to treat three-body problems. And in this group photograph, in the front row, second from the left, is Professor Mitra. And of course, the first person on the left there in that row is Professor Indranil Mazumdar. Next slide, please. And just a few more pictures featuring Professor Mitra at that session, and including, for instance, tomorrow morning speaker, Professor Vari, and Chandu Warke, another very fine nuclear theorist who was for many, many years at TIFR, and again, one of the great teachers of all of us. And below, you will see that among the Russian physicists who participated, there was Fadeev, Efimov, whose name will come up again, and Belyaev in that picture, and one more picture of Professor Mitra on the lawns of TIFR. So just as a historical thing, and in 2010, as I said, we actually ended up with Professor Mitra talking very seriously about these three-body systems, whether in atoms or in nuclei. Next slide, please. So for the physics part of this talk, what I wanted to talk about are certain themes, and in particular, the role that the 1/r² potential plays in quantum physics, both in quantum binding and in the breakup. So at small and large r, this 1/r² potential you will see as a recurring theme in my talk. And in particular, when that potential is attractive, I'll come to this later on, you can also have quasi-bound states in that potential. Another aspect of this is, of course, these are fairly high excitations for any system, whether in atoms or in nuclei, and therefore there are resonances. These states are mostly quasi-bound resonances, and they have some very interesting asymmetric resonance profiles, which have been called Fano profiles. And so that's another theme I'll touch on. And then there is the role that the scattering length plays in all this. And in particular, I think in this conference, we're not talking much about BCS or the BEC, the Bose-Einstein condensates, but the whole condensate experimental thing has blown up because of this tuning ability that we have with scattering lengths. And I'll come to this very briefly about three-body bound states. And then finally, as I said, in nuclear physics, there are, of course, very neutron-rich species, again, with many radiation nuclear facilities, which we built, FRIB, and so on. There will be even more of these that will be studied, and there are going to be some very interesting sort of three-particle states, typically now 2 neutrons, and the rest of the nucleus. And of course, the interesting thing in all this is that this has to do with 1/r² and very simple quantum physics of the 1/r² potential. So whether it's atomic, molecular, or nuclear systems, we're going to see the same kind of physics. Next slide, please. Now, of course, when we think of the 1/r², it actually arises, of course, from the kinetic energy term. But in a three-dimensional problem, as in the very first courses in quantum physics, we will think of it as the angular part of the kinetic energy. Of course, classical physics as well, that's the angular momentum squared divided by the twice mr². Now, this is, of course, a repulsive potential at small r. And in a sense, it is the key for avoiding collapse of all the particles into a simple sort of point. Whereas at large r, in particular, as I said, when it's attractive, not in this particular example of purely repulsive, it holds low energy particles from penetration or escape from the potential. Now, in classical physics, of course, there will be a collapse for this angular momentum 0, but for any angular momentum or even zero angular momentum in quantum physics, the very presence of this fundamental constant h bar and the physical dimensions it has is that any particle of mass m is always going to see an energy contribution. We can think of it as a potential as well, as we do, as h bar squared over mr squared. And of course, very familiar to everybody is the basic idea that the stability of the atom, of course, comes from the balance between this 1 over r squared potential repulsive or a positive term and the attractive 1 over r of the Coulomb potential. Now, this, of course, is what started the whole field of quantum physics in 1913. Of course, the full-blown mechanics came in 1925. We are celebrating the centennial of that birth of quantum mechanics this year. Now, the same idea of the angular momentum 1 over r squared term is, of course, what is responsible for this very famous law that is known well through atomic and nuclear physics, called the threshold law that may I go to the next slide, please? So whether it is for energy slightly above threshold, you can think of, so if you look at this sketch, whatever the potential, whether it is some short-range nuclear potential or particle physics potential, or even if there is a Coulomb long-range potential, if you think about the angular momentum barrier, and then any small energies, so whether just above breakup threshold or just below for high excitation, is going to have this angular momentum potential also stretching out to large r. And so if you think about a particle which, say, has been excited by a photon or by a gamma ray in the case of nuclei to slightly above breakup, it has to tunnel through this barrier. And in fact, it's a very nice little exercise to show that the WKB penetration formula for small energies, the energy parameter is, of course, this k squared. So for small energies, we look at the barrier penetration, typical exponential penetration through it, that in fact gives this k to the 2l plus 1, as pointed out by Wigner a very long time ago. And so it is an inescapable, it's a universal thing that you would see. You would see it in elastic scattering phase shifts where the particle comes in and then has to go out, or in any inelastic cross-section which starts at small r and still has to tunnel out. And of course, the smaller the energy above breakup, the longer it has to tunnel through and the larger the barrier, and that is the suppression, which goes like k to the 2l plus 1. Next slide, please. Now, if you have an attractive potential, in addition, I'll come to this in a minute, where it might arise from, but suppose for a moment I have a negative 1 over r squared potential effect, then of course it will combine with the angular momentum, and in a sense you can describe this as a complex angular momentum now. So instead of L, a lambda, and it'll have a real part and an imaginary part, and that is again related to this potential, to this parameter A. So whether the parameter A or the parameter alpha, equivalently, we can think about such a potential. And then there will be a number of bound states. And in fact, in any attractive 1 over r squared potential, you will not always have an infinite number of bound states as you do with the Coulomb potential, which is even longer range, 1 over r. But you can have, depending on the strength parameter, even an infinite number of bound states. So 1 over r squared is actually the dividing line among all power law potentials, as again we study very early. It's true also in classical physics that any other power of r will always have a finite number of bound states, if at all, whereas 1 over r squared, depending on the strength, this parameter alpha, can have either a finite or an infinite number. Now, whenever you have an infinite sequence, one of the simplest ways of thinking about it is in terms of the trigonometric functions, sines or cosines, because the sine of something equal to 0 gives this equally spaced pattern of n pi eigenvalues. And it's simply a matter of scaling that what goes into this, brackets here, determines then what is the relationship between the energy and the subsequent n values of the sequence of states. So for instance, with, again, the energy as essentially this parameter kappa, and now we are talking of bound states, so it's negative. So if you look at that parameter, in the Coulomb potential, what sits in this sign is simply the charge of the nucleus divided by that kappa. So of course, if that is equal to n pi, this is an atomic units of h bar and m and e as 1. And then, of course, this translates into the famous Bohr formula. 13.6 eV is the energy scale, and then there's a z squared over n squared. So the familiar Bohr spectrum. Now, if you have a 1 over r squared potential, again, in the Fano group, we developed a whole sequence of things we call quantum defect theory. What goes into this sign brackets here depends on that parameter alpha in this following way. Again, the energy parameter sits here. There's also this. It's a slightly more complicated expression than this simple Coulomb expression. But again, this equal to n plus a half pi gives you the energy values. This time, the energy values actually stack up even closer and closer to threshold. Instead of a 1 over n squared pile up, they actually go exponentially to threshold. But you can have an infinite number of bound states. Next slide, please. And next slide. Yeah. Now, in any n particle problem, you can have similar considerations. And in fact, a 2-electron problem is really a 6-dimensional problem. And you can think of it in terms of some overall radius r. And then all the angular part will, again, simply a matter of dimensional, will have a 1 over r squared. And now I won't go into the details here, but it is here that these parameters here depend, of course, on the number of particles. For the 3 bodies, this is number, of course, 6. And then the kinetic energy term, the angular part of it, has this very interesting structure. For d equal to 2, it's attractive. For any dimension larger than 3, it's always repulsive. Next slide, please. Now we talk about resonances in physics, and resonances typically, again, the cross-section of something that you're looking at, whether elastic or inelastic, will have an energy parameter, which is the position of the energy with respect to the resonance position measured in half-widths. And there is the so-called Fano shape of the resonance, which has the Breit-Wigner 1 plus epsilon squared, which we normally think of, but really has another contribution in the numerator here with another parameter called the Q parameter. Next slide, please. And let's skip this slide. Next slide. Now, this gives the characteristic shape of these resonances, and they typically have, it's an interference pattern in quantum physics, and so there's a dip at some point, and then there's a rise. And it depends on the value of this Q on what the shape looks like. So there are really 3 parameters: the resonance position, the width, and this Q parameter. Next slide, please. Now, the scattering length, I also mentioned. Let me very briefly introduce this parameter. It's a key parameter that, again, many are familiar with. And in the simplest case, if you have a 3-dimensional radial potential, and let's say L is equal to 0, let's say that the potential is very weak, then in fact, there's only the d squared, dr squared, and the kinetic and the energy term, which is a constant. So of course, u of r either this has a linear dependence or a constant. So in the vicinity of energy small, you'll only have a linear dependence of the wave function. So inside, it may have come up to some value going up, say, linearly. And now there are 2 possibilities. You can either attach to something which is rising up or to something which is going down. If you attach to something which is rising up, later on it can only oscillate. You will only have continuum states or scattering states. But if you attach it to something which is falling off, then you can, of course, also attach it to a dying exponential and have a bound state. So one single parameter, and this was particularly beautifully brought out by Fermi, this concept of the scattering length, it plays a role in H minus, it plays a role in deuteron. Again, I don't want to get into that here, but next slide, please. And in terms of this, there's a very interesting effect that some of you are certainly aware of, called the Efimov effect, that if the scattering length becomes very large, which means that you are only just bound or not bound for the pair interaction, then when you have 3 bodies, even though the 2-body pairs are not bound, the number of 3-body bound states actually can go even infinite. So there will be three-body bound states, which depend on that parameter, the scattering length A, and other, like the short range in this case of the nuclear example. And the number of bound states actually goes up. Of course, it goes up very slowly, logarithmically, with this ratio. Now, this was predicted a very long time ago, but wasn't observed in any nuclear or atomic system till relatively recently. And next slide, please. Just to show you the experimental observation of this, in the case of cesium trimers. Two cesium atoms don't really form a bound state, but they're almost on the verge of binding, and trimers, three cesium atoms, and this is where the first ephemeral states were experimentally observed. And you see again these very interesting asymmetric profiles, and these are some of the references. Next slide, please. And with Indranil Mazumdar and Professor Bhasin, we looked at this system for 20 carbon. Now, as you can imagine, carbon is usually 12 or 14 maybe, but 20 carbon is a very neutron-rich species. In particular, you can think of it as 2 neutrons and 18 carbon, which is already a neutron species, a neutron-rich species. But neither of 2 neutrons bind, but they're just short of binding, as we well know. And the neutron doesn't bind to 18 carbon, that's that odd-even effect. But the 3 bodies have ephemeral states. And here's an example again of an asymmetric resonance associated with these ephemeral states. Next slide, please. Next slide. This is simply to capsule that the doubly excited states we study in things like helium, so 2 electrons in the alpha nucleus. And so here is the ground state, 1s squared at 79 electron volts of binding. And then all the singly excited states were only exciting 1 electron at a time, leaving the other as 1s. And they go up to 25 volts roughly. And then there's the 1 electron continuum. But if you now pop both electrons into the 2s squared, even the very lowest, n equal to 2, or to the 2p squared and so on, those states lie way up here. For atomic physics, 60 volts is a very high energy. And these states now are embedded in this background continuum. And so they show up as resonances. The same situation here of 18 carbon plus 2 neutrons. And here again, in the vicinity of this energy breakup, you will see these ephemeral resonances, the one that you just saw in the previous slide. Now, the next slide is my last slide. And this is to make the other end. And here again, come back to more close to Professor Mitra's work. And that is that for a long time, of course, between nuclei and nucleons, we have recognized that there is a repulsive barrier at short range. And those of us who were graduate students in the 60s or 70s, there was a lot, MIT models and various other models, soft core, hard core, and so on. Now, of course, we understand this in modern terms, in terms of the fact that 2 nucleons are actually, at a minimum, the 6 basic quarks, but really many other quarks and gluons that constitute the system. But in a sense, this is a very many particle problem. But there is one radial parameter, r, that you can think of. And then you say that in terms of that r, at small r, if there is always a 1 over r squared, that is a kind of a repulsive potential. And that will, of course, lead to, again, I won't go into the details of this, into various things in how it shows up in the cross sections. So to summarize, and coming back to, as I said, to something much closer to the kind of work that Professor Mitra was associated with for a very long career, 1 over r squared is a potential which has some very interesting effects, both at small r and at large r. And we have many nice examples, both in atomic systems and in nuclear systems. And this, of course, is a nod that I make at this point to one of the great physicists of 3-body quantum physics, and that is Professor A.N. Mitra. Thank you very much for your attention, and I'll be happy to answer questions.
Thank you very much, Professor Rao, and let us applaud and thank Ravi once again for this very beautiful exposition of a very interesting problem of 3 bodies, which also, I mean, as we all know, has been said many times, Professor Mitra made pioneering, almost literally started that subject way back in 1960 and carried forward with his battery of very, very bright students. So it is open for Ravi, finished 3 minutes in advance, so we will have a lot of time for discussion. Any question? While I search for any raised hand, if you have any question, please, you can start. Anybody?
So, excuse me, I'm Numaishi. At some point of time, there was a expression and a sentence that if dimension is more than 3, it becomes negative or something. So what is in that context? Please repeat that one.
Okay.
Dimensions.
Yes, I think what you're referring to is that if you look at the Laplacian in higher dimensions, there is, of course, a purely radial part, which will have the second derivatives d squared over dr squared, and then the dimension -1 divided by r of ddr, the linear term. But then there's all the other coordinates are angles. And if you look at that, which is like a kind of grand angular momentum, which is in fact the term we call it, squared over r squared, h bar squared over 2m, of course, is the potential from all the angular motion. Now, of course, in 2 dimensions, that angular motion is simply little m squared, whereas in 3 dimensions is the famous L times L plus 1. But in any other dimension, when you finally look at this effective potential, it has a d minus 1 times d minus 3 over r squared, as you had in one of my slides before. I'm not going to call back for the slides because that often messes things up. So as you can see, for any d greater than 3, that is a purely repulsive. For d equal to 3 or d equal to 1, of course, it doesn't exist. But for any other, when you remove the linear term, there is always going to be this repulsive 1 over r squared. So in any collection of many degrees of freedom, whether many particles or even a particle in higher dimensions, at small r, there is an effective 1 over r squared, which in a sense is saying that it prevents things from getting too close together. After all, again, going back to 3-dimensional intuition, if you have angular momentum, you're kept away from the center. You're going to be kept away because there's a kind of a repulsion or a barrier, if you wish. And so that is exactly the same thing for any dimension larger than 3. And it's always going to keep you away from very small r.
Thank you. Thank you.
Professor Kaushal.
Can I add my observation? See, we have 1 upon r square potential in gravitation. We have 1 upon r square potential atomic level. We have 1 upon r square potential quark level also. See, confinement and then short distance. We also have intensity between 2 light objects. That also vary. So we say that nature likes 1 upon r square potential. This is general observation. Secondly, when you go to the classical equations of motion for a radial equation, even in 2 dimensions, then you find that only for n is equal to 2, you get stable orbits. Yes. If you depart even a decimal place, this side or other side, system is unstable. So mathematically, we do analysis of the stability. Nature is stable only with this. So perhaps God likes 1 upon r square potential. Thank you.
Now, I will not get into the latter part of this, but what you just mentioned before. Now, first of all, the gravitational and so on you mentioned are actually 1 over r potentials. The forces are 1 over r squared. But when we are talking of 1 over r squared, I think you're right where you said that only for 2 dimensions, again, go back to this term that I said, d minus 1 times d minus 3. So for d equal to 2, that has the opposite sign. Whereas for d any larger than 3, it's always positive. For d equal to 2, it's negative. So what you said about the 2 dimensions is correct, that 2 is peculiar in that respect. I think Professor Panchapikeshan had a question.
Yeah, I wanted to ask, can you hear me?
Yes, I can, very well.
Yeah. I just wanted to know what special role does the separable potential play in the Mitra's discussion of these problems? Separable potential.
That's interesting. I think the special role that separable potentials usually have in physics is they lead to one state distinguished from the rest. So this is the famous plasma mode that if you, for instance, it's a very simple thing. If you have n degenerate states and you give some kind of coupling between them, say equal coupling or first neighbor coupling, then one state gets distinguished from the rest. Sometimes it's the ground state, which is distinguished from the rest. In nuclear physics, that is what it is. The nuclear physics, the ground state is separate from the excited states. And that's, of course, because you have an attractive potential. And the same thing in BCS. There is one state which is distinguished for a many-body state, and that has this gap, and there is your superconductivity. Now, if the basic potential is repulsive, as for us in atoms, that distinguished state is actually very high in the spectrum. It's the highest state which is distinguished. And that is the state right at this breakup threshold that I talked about. And my PhD thesis was actually to extend Wigner threshold laws and so on to three-body problems, because Wigner had pretty much solved the entire two-body problem, but to three-body problems, and in particular with Coulomb forces of interest to us in atomic systems.
Thank you.
Any other question, comment? Okay.
So thank you again to all the organizers for including me in this.
Thank you so much. Any question?
I have a very naive question.
Sure.
Could you
you were saying that with this 1 by r square potential, depending upon the strength, you can you can have a finite number of bound state or infinite. So I have a very naive question, like, can you build a system with very highly separated two ground state, and you can use it for quantum computing purposes, qubits?
Well, it would be a very contrived system. I mean, we have many other simpler examples of two-level systems, and those will be the platforms for quantum computing. But since you asked the question, it's all a matter of scale. If you have bound states, it's a matter of the energy scale that you have in mind, whether you can think of just two states that you isolate as of interest. And of course, what we can always do now, particularly in atomic systems, because we have these very good lasers in specific domains, we can always tune the laser to just those two states. So even though there's an infinite number of other states around, for all practical purposes, it's just two levels, and that's our qubit, a single qubit. So in fact, the ion qubits, which is one of the platforms being investigated, aside from Josephson junctions and so on, works on that basis, that you take a laser and tune it to two levels of the ion, rubidium plus or whatever, for instance, and that is your qubit.
The reason why I'm asking is, can we make it more fault tolerant, interferences from the environment, can we make it?
As a youngster, perhaps you can work on that.
Okay, thank you very much.
For your questions. You can always email, and Ravi is always available to hear this.
Yeah, the problem is
and for discussion. So I now declare this session